Hello and welcome to today's physics lecture. Today we shall be discussing about EM induction continued from the previous topic or lecture where we have discussed about the factors affecting the mutual induction. Now there was a factor which was affecting the mutual induction which was stated as the angular orientation between two coils. Right? Now we would like to take a look at that. If, for example, one loop is being kept like this and another loop is being kept like this. So, for example, we say this one as the primary loop and this one is the secondary loop, which means that now the primary loop and the secondary loop are both mutually perpendicular to each other, right? At that circumstances, the mutual induction will be the least or minimum. The second scenario is that this is the first scenario. The second scenario is that if we are taking up two coils as such that the primary coil and the secondary coil are parallel to each other, in that circumstances, whatever the mutual inductance which will occur on the secondary coil, that will be intermediate. Why are we calling it intermediate? We shall try to understand it a bit later, but this thing that is intermediate, what it is going on, say for example, the value it came out to be as X, right? The value of the mutual induction in the secondary coil is now X. And we want a mutual induction in this coil of, say, the secondary coil as such that the value of the mutual induction now to be increased mu times, right? So we want a mutual induction in the secondary coil equivalent to mu multiplied by X. So in this third scenario, if we are going to take, this is actually an insulated type of iron core. This is insulated iron core. Now, why is it insulated? Because now we are going to place this is, say, the primary coil wound around it, and another coil, the secondary coil, wound around it likewise. So this is the primary coil and this is the secondary coil. Now we are saying that this is wound around an insulated iron core but not on a simple iron core. Because if it is not insulated, then the eddy currents shall occur over here as was discussed previously. So we need to laminate and insulate this iron core, right? So as to avoid and minimize this eddy current effects. So over here the value will be equals to mu x, the intermediate. This will be the maximum. The maximum value which is equals to mu multiplied by x, where the mu is basically the permeability of this medium of iron core. Okay, so what is mu? Mu equals to permeability of iron core, or to be precise, of the insulated iron core. Right? Now let us understand that why is it minimum, why is it intermediate, or why is it maximum. Right? Say for example in the primary coil now, the current is being induced over here. The current flows like this. If the current is flowing like this, say for example, we are taking the current as per the twist of our right hand, these fingers, right? So it happens as such, we will see that either this magnetic field will be in this direction or in this direction, depending upon the direction of flow of the current in the primary circuit or in the primary coil, right? So we can see that either this B will go on this side or on this side. There is no coil that will be actually trapping this B directly. In case it is 90 degree, right? So over here the trapping of this B and subsequently the dot product of this B vector multiplied by the A vector or the magnetic flux will be the least. So the change of magnetic flux with respect to time or d phi by dt will be the least again. And if that is the least, the induced EMF that will be produced in the secondary coil would be the least. Right? Applying the same logic, we can say that either this primary coil, the B will either go in this direction or in this direction, and if the secondary coil is parallel, it will be directly trapping this B, right? So it will be getting the maximum out of the phi, because phi equals to the dot product of this B multiplied by the area vector, right? So over there the phi will be the maximum, and the rate of change of phi with respect to time will be the maximum again. And as we know that the rate of change of phi or the magnetic flux with respect to time is basically equivalent to the induced EMF. So the induced EMF will be the maximum, and that is the reason why this could be the maximum value of mutual induction. But it could have been the maximum if there was no possibility of increasing any kind of way to increase this value of mutual induction, right? But fortunately we found out a way that how to increase this, and that is the reason why this is now termed as intermediate instead of maximum. The maximum will be, it will be the mu times, it could be increased. This same thing, these two coils, if they are now wound around an insulated iron core, where the eddy current effect could be minimized. In that circumstances, if this insulated iron core has got a permeability of mu, then this value of this mutual induction would be the maximum equals to mu multiplied by N. Right? Now, we are saying that some coupling is happening over here. It is coupled. Or in any case, the coupling could happen. Right? So, we are going to understand about the coefficient of coupling. coefficient of coupling. The coefficient of coupling is basically the measure of its coupling between two coils, right? And it is denoted by capital K. The value of the capital K, it is actually K equals to the mutual induction between any of these two coils, right, divided by this coil will be having its own self-inductance of L1 multiplied by the self-inductance of the secondary coil L2. So this is the value of the coefficient of coupling, but it may be noted that the coefficient of coupling is always lesser than 1, right? Which means that the value of square of the mutual inductance between two coils will always be lesser than the product of their self-inductances. So we can arrive at the conclusion that m square is always lesser than L1 multiplied by L2. Looking at this formula, we could now understand that in self-inductance or in self-induction, only the self-induction phenomena shall take place because there is a single coil. But in the process of mutual induction, there will be two kinds of induction. Primarily, the self-induction between the two coils individually, because they are individual coils. If this coil is not over there, there will be a mutual, like a self-induction between on this coil, and again there will be a self-induction on this coil, and if they are kept together, there will be a mutual induction between these two coils. So in mutual induction, basically both the self-induction as well as the mutual induction takes place, right? Now we shall be looking about the mutual induction of a plane coil. Of two plane coils, right? Because there would be two plane coils. If the two plane coils are kept as such that one coil is on another coil, like this. Say this is a coil, right? And on this coil we are keeping another coil now, right? So this is a plane coil one, and we are keeping it on another coil. So the mutual induction of two plane coils, as we have seen in the case of self-induction, that diagram was something like this. The current IP right, this is the primary current. This is say the radius of R of the primary loop, right? And for example, we take as NP equal to number of turns in primary, and Ns is the number of turns in the secondary. This is for the primary coil and this is for the secondary coil, right? So over here we could write as phi will be equals to Ns BA cos theta. Now as we have kept one coil over another, thus the theta over here would be 0, and likewise the cos 0 will be equals to 1. And we could say this radius of the primary coil as Rp, right? Over here the value of B, what is it? For this kind of things, we have seen it before. This will be replaced as Ns. B over here will be mu naught N, the number of turns now for the primary, multiplied by I divided by 2 Rp multiplied by A, and the cos theta will be 1, right? Now, why have we taken over here this as Ns and why have we taken over here as Np? Because we are dealing over here with this phi, the value of which will be the magnetic flux in the secondary coil. So, when we are going to find out the magnetic flux in the secondary coil, then the number of turns in the secondary coil shall count. While on the other hand, this B is because of the primary coil. Because the current is flowing in the primary coil only, then only the B is produced, the phi is produced, right? So this is because of the primary coil. So mu naught N of the primary coil, number of turns of the primary coil, multiplied by the I or the current it is flowing, we should write it as IP, because this is IP, divided by 2 Rp multiplied by A, the area of the cross section, right? Or the area of this region. Now also we know that phi, we could replace it by the formula, as we know that phi is equals to M multiplied by I, right? So over here we could write M multiplied by IP will be equals to mu naught NPNS divided by 2 Rp multiplied by A and multiplied by I. Now we could well see over here, this will be IP, this one, and we could well see over here that this IP and this IP will get cancelled out. So the left out expression now will be M is equals to mu naught multiplied by NP NS multiplied by the area divided by 2 Rp. So this is the expression for the mutual inductance or the mutual inductance of two plane coils when they are placed in such a position. The main noteworthy point is that we have to understand that where we are going to put NP and where are we going to put NS, right? So over here we have understood about the angle orientation, that how this factor of angle orientation affect the mutual induction. Then after we have understood about this, the coefficient of coupling K, and we have understood that N squared will always be lesser than L1, L2, which means that in due course of mutual induction, the self-induction process will also take place simultaneously. And after that, we have taken a look about the mutual induction of two plane coils, where the expression comes out to be like this. Thank you.